Before I move on to the examples, let's have a look at their graphs as well. This is the graph of growth, while the other one, this is the graph of decay. You can see from the graphs that the function is increasing here, while the function is decreasing in this scenario. So a couple of things that you need to remember for now. I will talk about these graphs later in detail in one of my videos, but for now, I want you to familiarize yourself with these basic shapes, with these parent shapes. The most important thing is the reference point. For both the graphs, the reference point is 0, 1. Now, why is that? You replace x with 0, what do you get? Y equals 2 raised to power 0, which is 1. So you see the graph basically starts from 0, 1 and not from 0, 0 like a straight line, or you can say a quadratic equation where the turning point of x square is 0, 0. Similarly, you replace x equals 0 here, you will get y equals 1 and not y equals 0. So the first thing to remember is the reference point. The second is the asymptote. What is an asymptote? It's a line that the curve reaches as it heads towards infinity, but it will never reach, it will never touch that line. This is very important. In this scenario, y equals 0 is our asymptote. You take any value, you will never get an output of 0. You will get very close to 0, but not exactly 0. This is very important. Similarly, in this scenario, you keep increasing the value of x. You go to infinity. The value will keep dropping, but it will never reach 0. That is very important. That is the reason the range of both the graphs says this: y is greater than 0 and not greater than equal to 0. Please remember this thing. So what's the domain of these graphs? If I talk about the domain, look at the positive side, look at x equals 0, look at the negative side. The output is there when we talk about the positive axis. At all these values, we have an output. The graph exists at 0 as well, and the graph exists on the negative values of x as well. So that is why the domain is x belongs to all real numbers for both these graphs. Now, let's move on to the examples. For her 8th birthday, Shelly's grandmother gave her a full bag of candy. Shelly counted her candy and found out that there were 160 pieces in the bag. This is our initial count. This is the value of A. As you might suspect, Shelly loves candy, so she ate half the candy on the first day. It's definitely a decreasing function. Then her mother told her that if she eats it at that rate, the candy will only last one more day. So Shelly devised a clever plan. She will always eat half of the candy that is left in the bag each day. Important tip, this is our basically decay factor. She thinks that this way she can eat candy every day and never run out. This is interesting, I like the plan. How much candy does Shelly have at the end of the week? Will the candy really last forever? Interesting. I have already drawn a table of values for you. So let's have a look at this. So on the 0th day, when she's given the candies, we have this number 160. So our equation is y equals ab raised to power x. We know the initial count, that is 160. Now we need to find out b, that is our decay factor. So let's have a look at the table. On the first day, she eats half of the candies and we are left with 80. On the second day, she will eat half of the remaining candies, that will give us 40. On the third day, you take half of this and you have 20. You keep repeating this process, and by the 7th day, you will get 1.25 candies. So what is happening? The decay factor over here is this, half of the candy that is left. So b equals 1 by 2. Our equation would look something like this. We have y equals 160 into 1 over 2 raised to power x. You see, this b is a fraction between 0 and 1, so it has to be exponential decay and not exponential growth. Now, let me have a look at let me show you the graph of this function as well. So the graph basically looks something like this. We start with 160, the candies keep decreasing and ultimately they reach very close to 0. Now, this is an interesting part that we need to understand. Will the candy really last forever? So we saw that by the end of the week, she has 1.25 candies left. So there doesn't seem to be much hope for that. But There's always a but involved when we look at it mathematically. If you look at the graph, you will see that the graph never really gets to zero. Remember, y equals 0 is the asymptote here. And what is an asymptote? The line that the curve approaches as it heads towards infinity, but never touches that line, never touches that point. So theoretically, there will always be some candy left. Let me write it like this. There will always be some candy left, but Shelly will be eating very, very tiny fractions of a candy every day after the first week. This is the fundamental feature of an exponential decay function. Please remember this. Its value gets smaller and smaller, but never quite reach zero because of the asymptote. So the curve will never touch y equals 0 for a simple basic exponential growth or decay. Please remember this. Let's have a look at this past paper question. A radioactive substance decays at an annual rate of 13%. If the initial amount of the substance is 325 grams, which of the following functions f models the remaining amount of the substance in grams t years later? So our equation is y equals a b raised to power x. Our initial amount is 325. Now, what is the value of b? It is given in the question that each year the amount of the radioactive substance is reduced by 13%. So what's the remaining value? So the remaining is basically 87%, which is 0.87. So if you ever get confused, just look at the first year and tell me how much will the amount remain after the first year. So you will multiply this with 0.87 and not with 0.13. That is something you need to remember. So the equation will look something like this. Y equals 325 into 0.87 raised to power t. This is our equation, which is option choice A. Another interesting past paper question. The population of mosquitoes in a swamp is estimated over the course of 20 weeks as shown in the table. Which of the following best describes the relationship between time and the estimated population of mosquitoes during their 20 weeks? Increasing linear, decreasing linear, exponential growth, and exponential decay. The first tip that you have over here is this word, population. Remember I told you, whenever you come across words like population, bacteria, enzymes, compounding, and similar other words, we are looking at an exponential function and not a linear function, because the population increases or decreases exponentially. So you can definitely eliminate the first two options. It's not linear. Now let's have a look at the table. So in the 0th week, we have 100 as our population. So this is basically A, our initial count. In the 5th week, the population increases to 1000. So it's basically growth. Okay, how do we reach 1000 from 100? We are basically multiplying 100 with 10. Then in the 10th week, the population has increased to 10,000. How did we get this figure? We multiplied 1000 with 10 again. So you can see we have our growth factor as well. So the equation is y equals ab raised to power x. A is basically 100. B is the growth factor, that is 10. So our equation would look something like this. Y equals 100 into 10. Now be very careful with the exponent. So you see the mosquito population starts at 100 in week 0 and then is multiplied by a factor of 10 every 5 weeks. Every 5 weeks, not every year. So whenever you have a similar statement, you will have a fraction as an exponent. The exponent will be t over 5 and not 5t. It's very easy to understand this. Just replace the value and find your answer. Check your answer. When t equals 5, what's your answer? We have 100 into 10. 5 divided by 5 is 1. We will have 1000, which is completely fine. You see, in the 5th week, our answer is 1000. Let me give you a small tip. Whenever t is less than 1 and the population increases within a year, you will have an integer exponent. Remember this. So if it doubles or triples within a year, we will have an integer exponent. However, if the population doubles or triples in 2 years or 3 years, let's say t is greater than 1, it can be any number, then you will have a fraction as an exponent. This is an important tip that you should remember. Next question. The population of trees in a forest has been decreasing by 6% every 4 years. This is important. Every 4 years. See, I told you in this scenario t is greater than 1. You have a hint. It means that we will have our exponent as a fraction and not as an integer. The population at the beginning of 2015 was estimated to be 14,000. This is our initial count. If P represents the population of trees T years after 2015, which of the following equations gives the population of trees over time? So our equation is y equals ab raised to power x. We have our initial count, that is 14,000. What's the value of b? So it basically decreases by 6% every 4 years. So the remaining is basically 94%. And we always take this value, which is 0.94. So our equation would look something like this. P equals 14,000 into 0.94, the remaining amount, raised to power t by 4. Please be careful of this because it decreases by 6% every 4 years. T is greater than 1, which is option choice D.